Okay, Astronomy 1020. We are going to do our special homework assignment, one that was not originally listed. I originally had in mind to call this homework 8, but because it's between homework 7 and homework 8, this is special homework 7.5, okay? And this is a video that we're making in class today with our studio audience, the night students. Say hi, everyone. There you go. Oh my God, we're never going to get to this. All right, so here we go. The problems that we're going to be doing, hold on, I've got them on my phone, are problems from chapters 15, 16, and a special problem, the Doppler shift. So we have chapter 5, number 61. We have from chapter 15, number 58.
Are we section 103?
You guys are 102. The the online class is 600, I think. So depending on which section you're in. For you guys, you want to do 102. Okay, chapter 16 is 50 and 59. Notice, students, that that's only 4 problems. I decided to go easy on y'all this week.
So nice of you.
I know, I'm a hell of a guy. Now we're going to begin chapter 5, number 61, is on something we'll be learning about today called the Doppler shift. The Doppler shift is a method of measuring the velocities of stars by studying changes to their absorption lines. You'll remember that stars produce absorption line spectra, and these lines might relate to several different elements in the periodic table. If we focus on one of the lines, we know that in a laboratory rest frame, this line might have some characteristic wavelength. In the case of the hydrogen wavelength that we're going to be observing in today's problem, it's 121.6 nanometers. And this wavelength is what's known as the rest wavelength. This wavelength is the 2-to-1 transition of an electron in a hydrogen atom. So it's called the 2-to-1 transition of hydrogen. And its special name is Lyman alpha. That's what it's called. Now, the way the Doppler shift works is if a star is at rest with respect to Earth and the Sun, then the Lyman alpha absorption line will be at exactly 121.6 nanometers. However, it's possible for us to measure small changes in wavelength, either towards the blue end of the spectrum, and this would be called a blue shift in the observed wavelength, or a small change in the wavelength at longer wavelengths, and that would be called a red shift. These changes in wavelength are due to the Doppler effect. So let's draw an eyeball that represents the observer on Earth. And let's put a star over here in outer space. When a star has a velocity that is toward the observer, the wavelengths of the emitted or absorbed photon become compressed and shifted towards the blue end of the spectrum. Motion toward the observer creates a blue shift, and that usually means shorter wavelength. The other scenario is when you have an observer on Earth and a star that's moving away from the observer at home. Motion away from the observer will stretch out the absorption line, increasing its wavelength and shifting it towards the red end of the spectrum. This is something called a red shift. Red shift usually means longer wavelength. Now, we can translate these things into a velocity using the so-called Doppler shift formula. Let me slide this over.
Hey, you were prepared.
Oh, well, this is from our lab today. Okay. So the classic Doppler shift formula is a way of calculating the velocity of a star. It's the speed of light times the change in the wavelength divided by the rest wavelength. This is the Doppler shift formula. Now, if we expand upon this, we're going to be measuring the speed of light today in kilometers per second. It's a little bit more elegant to work with when you're measuring the velocities of stars. So I have the speed of light is 300,000 kilometers per second. And the change in wavelength will be the observed wavelength minus the rest wavelength in parentheses. And this, by the way, this thing here, it's called the Doppler shift. That's the change in wavelength. And that's divided as a percentage of the rest wavelength. I would like to note that if your velocities are negative, if it's a negative number, that's motion toward the observer. If your velocities are a positive number, that's motion away. All right, so that's a little background. With that in mind, Noah will read us chapter 5, number 61.
In hydrogen, the translation from level 2 to level 1 has rest wavelength of 121.6 nanometers. Find the direct speed and direct towards or away from us of a star in which this line appears at wavelength A 120.5.
Okay, let's slow down for a second. 120.5 nanometers. So what they asked us to do is they said we've got a rest wavelength for hydrogen, Lyman, and alpha. This is the observed wavelength. And our goal is to find both the speed of the star and also the direction, whether it's towards Earth or away from Earth. So, observed wavelength, rest wavelength, let's apply the formula. The speed of the star will be the speed of light, 300,000 kilometers per second, times, 120.5 nanometers minus 121.6 nanometers divided by a rest wavelength of 121.6 nanometers. Before we punch that, let's have a moment of thought. Is this observed wavelength class a blue shift or a red shift? It's a blue shift. How did you know that, Katie?
The only reason why I thought it was because our resting shift is 121.6 nanometers, and so it's the one that we observed 120.5 nanometers, and if you were to
Right. Well, in other words, this is a shorter wavelength.
yeah, it's a shorter wavelength.
So a shorter wavelength means shifted towards the blue. Is that motion towards or away?
Towards us.
That's right. It's coming towards us. So we already got that part, the direction part, right? Okay. Let's see if we can punch this in. Shoot. Well, it depends what you mean by a big number. What'd you get?
I got 36 million.
No, you didn't use parentheses. Let's go ahead and punch this in to our calculators, carefully keeping track of our parentheses. So first we're going to hit 300,000. Okay? Now we're going to hit the times key. Now we're going to hit open parentheses just above the 8. We're going to do 120.5 minus 121.6. Now we have to close the parentheses. That gives us our Doppler shift, negative 1.1. We're going to now divide it by 121.6. What do you got? 2 sig figs. 27? Negative 2700 V. Okay, cool. That sounds good to me. Excuse me here. Units?
No, sorry. So, no.
Kilometers per second. Nanometer minus a nanometer is a nanometer. Nanometer over nanometer cancel, right? So this. It's a speed, so it's kilometers per second. That's fast. Okay. Cool. Let's move on now to B. Second verse is going to be the same as the first.
121.2.
Okay. 121.2 nanometers. So this is B. The observed wavelength is 121.2 nanometers. So the velocity is the speed of light, 300,000 kilometers per second, times the change in wavelength, 121.2 nanometers, minus 121.6 nanometers, close parentheses, divided by the rest wavelength of 121.6 nanometers. Class, is this a blue shift or a red shift? Also a blue shift because it's a shorter wavelength. So this is a blue shift, and that means the motion is towards the observer. All right, can you guys punch this down without troubles? Huh? Okay, we could go with that, I guess. I would have chosen 2 sig figs. So, 900 and what? Hold on, let's round better, right? Or is that rounding right? Hold on. 300, yeah, 300,000 times open P, 121.2 minus 121.6, close P divided by 121.6. Yeah, negative 990, right? The 1,000 would have been perfectly acceptable. That's the kind of thing that I would likely do, but I don't know. We're going to keep 2 sig figs just for propriety, just to be proper. And the units are kilometers per second. Okay. Noah, part C.
121.9.
Blue shift or red shift, students?
Red shift.
And that means motion is away. I got an idea. Since this is the Doppler shift up here, let's calculate the so-called Doppler shift because it's easy. The change in wavelength of observed minus rest is 121.9 minus 121.6, and I'm pretty sure that's positive 0.3 nanometers, right? Yeah? So now we can make this a lot easier on ourselves. The velocity of the star is 300,000 kilometers per second times 0.3 nanometers over the rest of 121.6. It's nice to see it this way too, because you realize it's the percentage by which the line is being shifted times the speed of light. We should be able to punch that up pretty quick too. So that's positive 740 in units. And everyone else backs that up, right? Okay. All right, we got one last one to do, and that's part D. Do it over here.
122.9.
This is a longer wavelength. So it's a red shift. The motion is away from the observer. The Doppler shift, oh boy, what's 122.9 nanometers minus 121.6 nanometers? 1.3 nanometers, positive, right?
Yeah.
All right. That's our Doppler shift. And the velocity then is 300,000 kilometers per second times 1.3 nanometers as a fraction of 121.6 nanometers.
About 31.
Can someone else back that up?
Yeah.
We cranked it out. Huh? All right, so where'd you get lost? Can I help you, Sarah?
I'm really glad the Doppler shift.
Oh, right. So let me explain that. The Doppler shift formula is the speed of light times the change in wavelength over the rest wavelength. But when people talk about the Doppler shift, they're actually talking about that little shift in wavelength. So the change in wavelength, which we represent as delta lambda, in this case, when you subtract the two, you get 1.3. That number is called Doppler shift. One uses the Doppler shift to calculate the velocity. That's the Doppler velocity. Remember, what's shifting is the absorption line, the position on the spectrum. I could help deconfuse you if I know where you're getting confused. You need to be able to ask me. Well, I'm going to cover it in my lecture today as well. I'm going to do a demo. You know what? I think I know where you're getting confused. You're getting confused in the original concept. First, you need to know that stars, when you take a spectrum of them, they produce a rainbow with dark black absorption lines. That's what the spectrum of stars is like. So it turns out that if stars move towards or away from you, the wavelengths of those lines shift because of the motion of the star. The Doppler effect happens for audio as well as for light. For instance, when you hear sirens come by you in the city street, normally a siren goes woo, woo, woo. It's a sine wave, right? When an ambulance races towards you on a busy sidewalk, you can hear the pitch go up as it's Doppler shifted towards you. You hear the pitch go woo, and then as it passes by you, you can hear the frequency or the pitch get lower, right? So you can hear Doppler effects with audio, and it's the same thing except for light. It's very, very subtle because light moves kind of fast. So normally you'd be emitting photons like so, but when you're barreling towards the observer, it's going to compress the wavelength of light, and it's going to shorten in the case of illusion. Classic physics thing, it's called the Doppler effect. Wavelengths of light change when objects move towards or away. Just take some time to let it sit, okay? The idea is measure wavelength shift, get star velocity. That's the purpose, okay? It's a trick to measure the speed of stars. All right, let's move along here. Keely, do you have all this stuff down?
I just messed up on this.
I kind of changed my methods halfway through. Earlier, I was having us put in the new wavelength and the rest wavelength, but then I decided to have us just calculate this top part. So that, all right, why don't you get that part down? I'm going to start over here while Kaylee finishes that. So we're number 61 is down. And now we're going to move on to number 15. I think what I'm going to do is I'm going to read the questions because I'm worried that I listened to one of these videos earlier and the audio is really crappy on these cameras.
You saying garbage?
No, I'm saying you're wonderful. You did a wonderful job.
Tell me I did garbage.
Well, you know. What do they say in computer science? Garbage in equals garbage out. Okay. Okay. Let's see. This is number 58. Okay. The title is Calculating Stellar Radii. Sirius A, the dog star, has a luminosity of 26 solar luminosities. It's chapter 15. Oh, yeah, sorry. Okay, I'll get to that in a second. Yeah. Sirius has a luminosity of 26 times the sun and a surface temperature of 9,400 Kelvin. What is its radius? This is chapter 15. Stellar radii. We have the star Sirius, a luminosity of 26 solar luminosities, and a temperature of 9,400 Kelvin. Okay. This problem requires us to use a legendary formula known as the Stefan-Boltzmann law for stars. It's a relationship between a star's luminosity, its radius, and its temperature. It all hinges around the inverse square law. If I know the total luminosity, the total output of a star in all directions, I can use the inverse square law to find the brightness of light coming out of a square meter patch at the surface of the star. The inverse square law tells me that the brightness is the luminosity divided by the total surface area of the star, 4 pi r squared. But I also know that each patch of light is glowing because it's a black body. I glow because I'm hot. And therefore, I can equate this to the brightness in the Stefan-Boltzmann constant. The Stefan-Boltzmann constant times the 4th power of temperature. Solving this for luminosity, you get the Stefan-Boltzmann law for stars. 4 pi r squared sigma t to the 4th. This is a useful result because 4 pi and the Stefan-Boltzmann constant sigma, they are numbers that never change. So what it's really saying is that the luminosity of a star is proportional to the square of its radius times the 4th power of its temperature. Classic astro stuff. Now, normally, in this version of the formula, you would use MKS units. What is the MKS unit for temperature? Kelvin. What is the MKS unit for radius? Meters, because it's length. Now, that's the way that I used to do this with students, and that's the way I'm tempted to do it with you. What would be MKS units of luminosity? That's brightness, Steve. Brightness is watts per square meter. Luminosity is, it's the same thing you measure the luminosity of a light bulb in. No one knows what units you use to measure the light output of a light bulb? Alright, how many of you have fucking changed the light bulb before? Let's start there. Does anyone know what their name or favorite color is?
The language.
I'm gonna ask. I
The
know.
language.
I don't.